I see space as the only adventure that's around today. I mean, back in the 1600s, maybe a man could sail and he could go to unknown lands. But today, there's none of that. Today, space is, well, the final frontier.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its 5-year mission, to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
This is the first voyage of the Space Shuttle Enterprise. Its mission? To make leaving the Earth as easy as flying around it. To begin the economic exploitation of space. To open up the final frontier. Space Shuttle Enterprise is named for the Starship Enterprise of Star Trek. Unlike the Starship, the shuttle won't find new civilizations, but it may help found new civilizations. Human settlements in space, giant habitats like these, in which tens of thousands of people will live and work, exploiting the resources of space for the benefit of Earth. This is for the future. The space shuttle's roots lie in the past, in the old way of getting into space. December 1972, the night launch of Apollo 17, carrying the last men to visit the moon. It was the conclusion of a space program that had left many on Earth disillusioned, and by the end, bored. Apollo 17 was also a turning point for the National Aeronautics and Space Administration, NASA. It had put America on the moon, building for the task the giant Saturn V rocket, now a technological dinosaur. A new approach was needed. Head of NASA's Office of Spaceflight, John Yardley.
The Apollo program and its predecessors, Gemini and Mercury, had been basically designed just to get into space and to do specific tasks in space. We were actually learning if we could do it at all. It became apparent then, as we were landing on the moon, that we needed, if we were going to use space in any gross way, we needed a better means to do this. The Saturn V launches cost $200 to $500 million each. So the idea of the space shuttle came into being.
In September 1976, the theme from Star Trek heralded the space shuttle's debut at the Rockwell plant in Downey, California. On hand were 2 Star Trek regulars, Dr. McCoy and Mr. Spock. Star Trek fans in a letter-writing campaign had succeeded in having the first shuttle named Enterprise. And NASA, sensing a new and younger constituency for space, was happy to go along. The Enterprise is the first of 5 similar space planes or orbiters. Its first journey was across the Mojave Desert on its way for flight testing. Its extraordinary shape is the result of its extraordinary task, to be launched into space like a rocket, to operate in orbit like a spacecraft, and then return to Earth and land like a glider. The essence of the shuttle is its reusability. Each of the 5 orbiters is expected to make over 100 flights into space and back. The first flights piggyback rides on a converted jumbo jet, tested the shuttle orbiter's aerodynamics. To save weight, the Enterprise has no engines of its own to help it fly back to its landing site after a journey into space. And as a result, it's all but unflyable by a human pilot.
We're ready to go. Enterprise, go for time. There's 203.
The astronauts who will fly the shuttle orbiter have each practiced the task for months on a simulator. In this duplicate of the orbiter's cockpit, the pilots have learned how to handle a landing. In this case, a landing on a map of Edwards Air Force Base. The vehicle landed not a shuttle, but a TV camera mounted on a boom that follows the pilot's every movement. The real shuttle is extremely unstable aerodynamically. To keep it flying, a battery of 5 computers is needed to help the human pilot. Without these computers, the shuttle would be no more flyable than a brick.
There's touchdown at 1:38. Okay, end of run.
A small jet aircraft was modified to handle like the shuttle. It gave the orbiter pilots some first-hand experience at flying by computer and of approaching the runway at an angle 4 times steeper than ordinary aircraft. The shuttle will drop so fast, it would beat to the ground someone jumping from 20,000 feet without a parachute. The first free flights of the Enterprise came in the summer of 1977.
Phase 2 clear. Hey, we got a GPC light, lost the sync on 2, pushing over. And a big X on computer number 2. Enterprise, you cleared.
The tail cone on the orbiter is there to reduce drag on its first few test flights, allowing it to glide in at an angle much less steep than will be its eventual returns from space.
It is really tight, Bo. In fact, I think it's a little better than the old STA field. 40 feet. 30. 20. 15. Okay, the gear is coming down at 270. Getting some dust, 4 feet.
The test landings of the shuttle are on the 7-mile-long dry lake bed at Edwards Air Force Base. But when the shuttle returns from space, it will land here on a newly built 3-mile runway at the Kennedy Space Center, Cape Canaveral. NASA is recycling many of the installations built for the Moon program. The 400-foot launch towers designed for the Saturn V are being cut down to accommodate the shorter, stubbier shuttle. This will be the first true spaceport, where the shuttle will land, be refurbished, and readied for launch again. This is how it was first planned to launch the shuttle. The orbiter would be carried on the back of a booster rocket that itself had wings. After taking the orbiter to a height of 25 miles, the booster would release it. As the orbiter flew on into space, the booster would fly back for a landing at Cape Canaveral. This design would enable both orbiter and booster to be reused. But the size of the booster, much bigger than a jumbo jet, made its development costs immense. And cost had assumed a new importance at NASA.
Everybody knew we could design a shuttle. The question was, could we afford to build one? So cost throughout the program has been as major a function as design integrity, safety, and so on. Whereas in the past manned space programs, cost definitely was a secondary factor because money was no object in those programs.
So now this is the design we ended up with.
NASA's chief spacecraft designer, Max Faget.
In the launch configuration, of course, we have this arrangement here, which is compact from the standpoint of having it all together, and it's by far the smallest of all the configurations we've looked at. And this is, of course, what you would expect when we have tried to reduce the initial investment. We ended up with something small and compact. But it is a kind of an unusual configuration for a launched vehicle.
The shuttle's unusual design, the result of the cost compromises that have characterized the program, have made it a peculiar hybrid, part reusable, part throwaway. It is taken to a height of 27 miles with the help of 2 solid strap-on rockets. When exhausted, these are dropped and parachuted back into the ocean, recovered, cleaned up, and used again. The shuttle's own engines continue. The fuel for these engines is carried in an external tank that's half a football field in length. The tank is jettisoned just short of orbit and burns up on re-entry. The orbiter continues into space with small auxiliary engines. The design is unique and poses unique structural problems that center on the fragility of the external tank.
To begin with, structurally, it's sort of messy. This tank here is the core of the whole launch arrangement. The empty weight of the tank is around 70,000 pounds. Yet we're hanging very large, massive boosters on that tank. Each one of these boosters weighs like a couple of million pounds. The orbiter itself, fully loaded with its cargo, is going to be in excess of 200,000 pounds. So easily the lightest component turns out to be the heart of the structural arrangement. And that is a little worrisome from the standpoint of what might happen dynamically to the vehicle.
Not all the shuttle's components are being built in America. This is Bremen, Germany, where one of the contractors for the European Space Agency is building Space Lab. Space Lab is designed to fit into the orbiter and provide a shirt-sleeve environment for work in space. It will also have pallets on which telescopes and other instruments for observing Earth and space can be carried outside. The entire laboratory will be lifted as a unit into the 60-foot-long, 15-foot diameter cargo bay of the orbiter. The bay doors will be closed, and orbiter and Space Lab launched into space. In orbit, the doors will open, and Space Lab, remaining in the payload bay throughout the flight, will begin work. Its crew will transfer from orbiter to the laboratory through a tunnel. With Space Lab, the shuttle can carry as many as 7 people into space at a time, including a lot of people who have never been considered before, at least by NASA, as potential astronauts. Women have given NASA's doctors a problem. They've never had to deal with them before. Head of Life Sciences at NASA, Dr. David Winter.
It turns out it's a very interesting point that there's very, very little data on women, particularly in the types of environment we're dealing with. Most of the information we've used, of course, have come from the services, from the pilot training courses, and from the types of individuals who traditionally, in the past, and I have to qualify that now, have been in those courses. They've all been young men.
And young white men at that. But in an attempt to attract women and minorities into the expanded astronaut corps needed to fly and operate the shuttle, NASA has been exploiting its newly discovered Star Trek connection in its astronaut recruitment drive.
Hi, I'm Nichelle Nichols, but I still feel a little bit like Lieutenant Uhura on the Starship Enterprise. You know, now there's a 20th century Enterprise.
I feel like we have one Enterprise that was fantasy.
Along with actress Nichelle Nichols, the NASA recruiting film also stars astronaut Alan Bean and another shuttle orbiter simulator.
Looks just like my Enterprise.
Yeah, it does kind of. Well, I'll tell you what it does look like. It looks pretty much like the real shuttle orbiter.
I'm speaking to the whole family of humankind, minorities and women alike. If you qualify and would like to be an astronaut, now is the time.
Over 8,000 people have applied to be shuttle astronauts, from which NASA is selecting some 200 for further training. Some will be pilots, others responsible for payloads and experiments.
As we fly in the shuttle era, we will find different individuals on board the shuttle performing different functions, and our basic philosophy is to match the medical requirements to the function that the individual must perform. For example, for the pilot, which has absolute responsibility for the safety of the mission, we will expect one sort of standards. For the scientist or passenger in the back end of the shuttle, who has no responsibility for mission safety, we will not expect the same types of standards. And I have often stated among my friends and in the agency itself that I will not be happy until we can fly the 65-year-old astronomer. That is really my goal. Now, hopefully we can meet it. I don't know. I'll be very honest. I don't know if we can meet that goal. But I would very much like to be able to do that. And in some of my other moments, I'll say I want to fly the 65-year-old poet.
But poet or astronomer will share a hazard first encountered by the crew of Apollo 8 as they flew around the moon: space sickness. About 1 in 3 astronauts who've flown have suffered nausea and vomiting. And the problem is, tests on Earth can't predict who will be sick in space.
If, and here is the point, if we cannot resolve this problem, then we will have the potential of flying individuals on shuttle who have the opportunity of becoming sick. And of course we don't want this. We're flying relatively short flights early on in shuttle, 7 days, 10-day flights. I certainly don't want to have people up there who are going to be sick for 3 to 5 days. On the other hand, though, I'm rather optimistic that we have some new techniques now which will enable us, if not to predict, to prevent the signs and symptoms of the motion sickness problem from manifesting themselves.
This man is being spun in a rotating chair to make him motion sick. A few minutes of the treatment, with head movements dictated by the voice of a computer, will make even the hardiest sailor or airman nauseous. His reactions are monitored: heart rate, skin color, breath rate. Then, with the chair at rest, he is trained to relax and attempt to control the symptom that is the first warning sign of motion sickness. In his case, the symptom is decreased blood flow in his hands. NASA's Pat Cowings is training the subject to control the symptom by playing him the signal from a blood flow monitor, a method known as biofeedback.
I want you to keep this feedback tone on. It's a beeping sound. When the tone goes off, it means the blood vessels in your hands have constricted. You're not relaxed. Say to yourself over and over in a continuous verbal stream, my arms are heavy and warm, and the tone will come back on.
Pat Cowings has added several personal touches to the standard method of biofeedback training.
It's more than what's typically known as biofeedback. Some subjects respond very well to verbal instruction. It's the kind of feedback they're used to getting in the world all around them every day. Some people would rather just introspect and get into the signals that we present. We suit the needs of the individual. No tension. No tension. Be passive. Passive. Say the words with a rhythm.
Pat Cowings' success rate so far has been impressive. Of the 16 subjects she has trained, 14 could ride the spinning chair for much longer after training than before. They are able consciously and deliberately to suppress the symptoms of sickness.
This treatment deals only with the symptoms of motion sickness, not with the mechanism that induces the symptoms. But we found in some experiments conducted recently that subjects can control motion sickness symptoms under one provocative simulator type condition. They can also control them under another provocative condition.
Trained subjects who can cope with the chair can also cope with this machine, the VARD, the Vertical Acceleration Research Device.
Helmet. Slip it on. Got
it. In the VARD, subjects are shaken up and down for hours. And while riding the VARD induces a different kind of motion sickness than spinning in the chair, trained subjects can still survive it longer. This leads Pat Cowings to hope that trained subjects will be able to cope with the still different type of motion sickness brought on by spaceflight.
Since we deal only with the symptoms, we feel that the symptoms will probably be very similar in space, and the subject should be able to control them in space as well. But the final test will be to go into space.
But the shuttle has an even bigger test awaiting it that only going into space will resolve. Its economics. NASA claims the shuttle will bring down the cost of spaceflight dramatically. But that will be true only if there is enough work to keep the fleet of 5 orbiters busy. Early opponents of the shuttle doubted the business existed. A prominent critic, astronomer, and ex-astronaut Brian O'Leary.
My objection to the space shuttle in 1970-71 was that it was too big for the kinds of goals that NASA had at that time. The shuttle is a leftover from Apollo. People were used to making rockets and making bigger rockets and better rockets. And so from the point of view of the vested interest in space technology, that the legacy of Apollo, the space shuttle made a lot of sense. But in terms of pursuing rational goals, NASA sort of had it backwards. It was a very large transportation system which had a much bigger capacity than was necessary for the things that NASA wanted to do during the 1970s. It was a large truck, but with very little to put into it.
Today's critics of the shuttle still argue it's too big a space truck. NASA claims it will make spaceflight cheaper even if it doesn't run at full capacity. The shuttle's major job will be deploying satellites, placing in orbit virtually all the satellites which today are launched by conventional rockets. The shuttle can only achieve orbits a few hundred miles high, and many satellites, like those used in communications, have to go up to 22,000 miles, where they will hover over the same spot on Earth. These satellites will have their own rockets to push them higher once the shuttle has placed them in space. But filling the shuttle's huge cargo bay is a big selling job for NASA. Operating the shuttle will be much like operating an airline. NASA's Mike Smith.
My job is primarily in the area of the business side of operating this airline. I'm concerned mostly with the development of users for the space transportation system and see it as my responsibility to see that the people in the 560 mission model actually materialize and use the space transportation system. The tools, the business tools that I have available to me are establishing a pricing policy that has very unique incentives for people to fly on orbit, both for flying on the shuttle and in flying on Space Lab. A specific example is our Getaway Special. Here we have a 200-pound, 5 cubic foot satellite that will fly to orbit in our space transportation system for only $10,000. And that's a very unique price incentive. It's about a factor of 5 less than it would be if a person were to buy a normal flight.
But Getaway Specials aren't going to make the shuttle break even. To do that means finding new customers for space. And NASA and its contractors have begun a campaign to convince U.S. industry that space is the place to be. The sales pitch is that new things can be done in space. This experiment was one of several that showed how molten metals behave differently in weightlessness, meaning new materials might be created with properties valuable enough to justify making them in space. Head of the Johnson Space Center with control over shuttle operations, Christopher Kraft.
Space has an environment different than the Earth. It has zero gravity and a perfect vacuum which you can utilize if you so choose. I think that as people who realize that space is more routine, becomes commonplace, easy to get to, useful to those who want to produce products while there, you're going to develop a whole new set of clients that we haven't had before.
In that sense, we're providing brand new opportunities for the industrial community in the United States to develop materials and techniques and processes which are not now available on Earth, or in some cases haven't even been thought of.
One use of the shuttle that is just now being thought of is the building of large structures in space. The shuttle's ability to come and go to orbit, taking up modular units one at a time and adding them piece by piece, means that very large space stations could be built up in just a few shuttle flights. These space structures could be expanded with virtually no limit to their eventual size. Building large structures in the weightlessness of space is very much easier than trying to do the same thing on Earth. Max Faget.
It'd be a lot easier to build big things if you didn't have this annoying gravity here that makes putting things together difficult, because until they're firmly fastened together, they want to come apart. There's nothing to hold them there. Well, in the gravitation-free environment of space, you can assemble things without any concern of what's happening to the thing you're putting together until it's fully assembled.
NASA has already begun training astronauts in the tricky techniques of joining and handling beams and girders in weightless conditions, using a large swimming pool to simulate the weightlessness of space. While things have no weight in space, they still possess mass, and great care is needed to maneuver them, particularly when there's a shortage of handholds and footholds. But there may be even simpler ways of making big things in space, using sheet aluminum so thin it can be cut with scissors. Working with Christopher Kraft and Max Faget at the Johnson Space Center in Houston, Jack Kinsler.
If you want to start to make any sort of large space structure, you must think of the materials that are required and the idea of packing them in the most dense fashion possible. I have here a roll of 6,000th aluminum sheet, which weighs 25 pounds and is 140 feet in length. This particular roll is capable of making a truss much like the one in the background, which would be about 50 feet in length. However, before going into orbit with this material, we would preform it in the manner shown here and eliminate the excess material that is not required in the final product. We retain 2 diagonal tension straps, and then we reserve a section of material for subsequent beading and bending to get a compression member. One of the early models that we built is shown here. It consists of the side panels that we talked about a moment ago, joined to circular corner columns made of lightweight material also. In order to construct that type of model, we designed a machine that would fit in the orbiter payload bay. It's deployed into the vertical position, after which this lower section generates tubular columns, which are shown here. And then the side panels are deployed from rolls up here and fastened in this point right here, making a combined unit, a truss, which could emerge out of the spacecraft on a continuous basis. We figured this first machine at a speed that would produce a 1/2 mile beam in 2 hours.
This is another design for an automatic beam builder in space. It is fed by rolls of strip aluminum brought up by the shuttle. It too would extrude beams continuously, and several machines could build immense platforms, miles or even tens of miles across in space. But why should you want to? This is the main reason: a solar power satellite, a panel of solar cells several square miles in area that can capture the full-time sunlight of space and turn it into electricity. This energy would then be beamed down to Earth below as microwave radiation. On Earth, the microwaves would be converted back into electricity again. Seen from above the Earth, bathed in the sunlight of space, the solar power satellite circles the planet, always keeping its face to the sun. It is only briefly eclipsed by the Earth, and in its stationary orbit, it always remains above the same spot on the Earth's surface, delivering its energy just where it is needed. In this design of a solar power satellite, the sun's energy is focused onto huge boilers, which drive turbines to generate electricity. Building such mammoth structures in space to help solve the energy problems of Earth was originally the idea of just one man, and when he took his idea to NASA 10 years ago, they thought he was crazy. Peter Glaser.
After all, here was a total outsider coming into NASA, talking about a project which by all counts looks like the largest space project ever suggested. So at first we were skeptical. Can it be done? Should it be done? You know, the obvious questions. But I believe that after the first shock sort of wore off, both in terms of size of the satellite and so on, and they began to get into the details that are required here, they recognized what it really could do and how the technology that the space program has developed could be applied. And in a sense, it was an obvious way to go in order to get the most out of the experience that we have gained.
NASA's enthusiasm for solar power satellites isn't surprising. Here is a task which could more than match the capacity of the shuttle. It builds directly on NASA's experience with space, gives the agency a role in helping to solve a very practical problem, and could set the sort of dramatically visible goal NASA hasn't had since the days of Apollo. But the agency has learned the wisdom of caution and even the most ardent supporters of space solar power are careful in public not to let their enthusiasm for such a way-out project become too obvious. Christopher Kraft.
Yes, I do believe that it should be one of the major themes of the NASA program. That isn't to say that NASA believes that space solar power today is the solution to the energy problem. We think it has promise. We think it should be worked on. We think it should be worked on a lot harder than we have been working on it, and that the country ought to make a reasonable investment in that kind of an energy system.
This is NASA's Goldstone dish. The agency has recently used it to send energy via microwaves across a mile-wide valley near Los Angeles. The energy lights up a bank of headlights, but there are concerns about the safety of beaming microwaves at Earth from space.
As far as the safety of the microwaves, once they're here on Earth, we probably don't have as much of a problem because we can design the receiving antenna site such that the public is not exposed to microwaves, and that in any case, the exposure to microwaves would meet the lowest future international standards.
Glaser claims that farming, for instance, could continue safely under the receiver for the microwave radiation. These receivers, one for each satellite, would have to be tens of miles across, and there would need to be a lot of satellites.
For example, just the United States would need about 112 satellites operating by the year 2025 to supply about 25% of our total electrical power needs. Now that's a huge amount of power that we're talking about, of course, but it also indicates that we'll have to build a lot of satellites.
And that's where the real problems lie. A whole new generation of heavy launch vehicles would be needed to put into high Earth orbit the thousands of tons of material needed to build even one solar power satellite. No one knows the environmental consequences of the rocket fumes from hundreds, perhaps thousands of such launches a year. And no one knows either the cost of such an immense project. The expense of simply getting into space all the materials needed to build solar power satellites could kill the idea before it even begins. But this man has an alternative that could eliminate the launch problem. Jerry O'Neill is a physicist with a brilliant reputation among his colleagues for his pioneering work on giant particle accelerators. O'Neill might have stayed in that abstract world, but he has always been intrigued by space. And then came the year of 1969.
1969 was an unusual year from a number of points of view. First of all, it was the year of the Apollo landings, a tremendously positive thing from technology. It was also a period of great violence in the Vietnam War, and technology and science were being blamed for the evils to which they had been put. It happened that year I was teaching the big freshman physics course at Princeton with about 350 students. I felt it was very important at that time to show to those students that it was possible for science and technology to be used for human good and not just for ill.
Disillusion with science was ironically heightened by NASA pictures of the Earth from space, revealing its beauty and apparent fragility. Spaceship Earth was becoming crowded, dirty, and short of supplies. Most experts saw things getting worse, but O'Neill asked instead a startling and extraordinary question.
In the long run, is a planetary surface, any planetary surface, really the right place for an expanding technological civilization?
The answer he came up with was no. For a technological civilization, space seemed to have many advantages over a planet. Energy in the form of sunlight is free, continuous, uninterrupted by night and weather, and essentially everlasting. The weightlessness of space means that huge structures could be built. Inside them, comfortable and Earth-like habitats could be created. Agriculture under these conditions could be extremely productive, and waste heat, a growing problem on Earth, radiated safely away to space. O'Neill's idea was for enormous inside-out worlds, spheres or cylinders over a mile across, rotating to create artificial gravity on their inner surfaces, powered by the ever-present sun. The scale of these space settlements, with masses of millions of tons each, makes even a solar power satellite puny by comparison. Bringing all that material up from Earth was clearly out of the question, which is where O'Neill had his key idea. Why use Earth materials at all?
Man, it didn't feel like this stuff was that hard. It looks like quite a bit of variety from here.
The lunar landings of Apollo showed what the moon is made of. About 30% metals like aluminum and iron, 20% silicon, 40% oxygen. Most of what you would need to build a space colony. Missing from the moon are organic, carbon-based materials, and water, though there may be water trapped near the moon's poles. But what makes all moon materials unique, by comparison with the Earth, is that they are already up there in space. The Earth, 80 times more massive than the moon, 250,000 miles away. Both Earth and moon sit in what are in effect gravity wells in space. The Earth's gravity well is 4,000 miles deep. That's how far you must throw something to get it off the Earth. The moon's gravity well is only 200 miles deep, so throwing things off the lunar surface is very much easier. To do just that, O'Neill came up with the idea of a mass driver, a giant catapult that would accelerate sacks of lunar rocks in buckets. The sacks of rocks would be hurled into space. The buckets would slow and return to be filled again. The track taken by the sacks of moon rocks would bring them to a point where they'd be caught, processed, and used to build space colonies. But there was one flaw in O'Neill's scheme. He didn't know how to build a mass driver. But it turned out that one already existed, though the moon was the last place its designers thought of using it, and moon rocks weren't intended as the cargo, people were. The MIT Magnaplane was a model of a high-speed mass transit system for use on Earth. The Magnaplane is cooled with liquid helium to a temperature at which it becomes superconducting. That means that an electric current set up in the coils within it will run forever because the coils have lost all electrical resistance. This current generates a powerful magnetic field around the vehicle. Placed in an aluminum trough, the vehicle is accelerated to high speeds by coils beneath the trough. Once in motion, the vehicle is lifted on its magnetic cushion and can travel without friction. The MIT Magnaplane project ran out of funding, but proved just what O'Neill was looking for. This is a model lunar mass driver being built at MIT. O'Neill spent a year there working with the designer of the Magnaplane and with a group of graduate students who did most of the work. One of these students is Kevin Fine.
It's not very often that a graduate student gets to work in a field in which he can apply basic knowledge. I mean, he can contribute directly to the design. Now, I feel like one of the Wright brothers or something, just beginning to work in a field that has a great future.
Kevin Fine's sense of being a pioneer is shared by the Magnaplane's designer, Henry Combe.
In many ways, this project is in the Wright brothers stage. You see, it's at the stage where fundamental analysis can still make progress. This is not the case in ordinary rocketry, for instance. We're working here with the basic fundamental principles of electromagnetism. We're working with Maxwell's equations, capacitors, condensers, coils, perfectly straightforward. In a way, it's a pleasure to work in a field where a student project such as this one can still make a significant impact and result in classical knowledge. Microswitch to make sure it triggers.
Nova filmed the MIT mass driver on the day of its first test.
5, 4, 3, 2, 1, fire.
This first model is not superconducting, but it still accelerated the vehicle to speeds of 80 to 90 miles per hour over a distance of 6 feet, an acceleration of some 25 G as compared to a sports car's 1/2 G. A real mass driver throwing rocks into space from the moon would be a mile or two long. But a mass driver throwing mass in one direction would itself be forced, like a recoiling rifle, in the other. So a mass driver, free in space, powered by sunlight falling on solar panels, would be pushed along like a rocket, but with some important advantages over conventional chemical rockets.
In principle, a mass driver applies all of its energy in one direction. You see, a rocket motor generates a lot of heat, which means it generates energy in all directions, and it uses only energy in one particular direction. It's therefore inherently inefficient. It stores energy very effectively, and this makes it possible to carry the fuel. But of course, that's all right for short-term operations, such as a launch from Earth. But for prolonged travel in space, you wouldn't think in terms of carrying chemical energy. You see, the mass driver is like a mule for the prospectors. It feeds on what it finds on the way. It uses electromagnetic energy from the sun and converts it directly with very high efficiency into kinetic energy of motion. It's the natural for space travel. It's an inevitable development in space travel. There's no question that that's the ultimate way to transport things in space.
One very suitable thing to be transported by a mass driver would be one of the asteroids that occasionally cross the Earth's orbit. These asteroids, if brought back to Earth, would provide a very useful supplement to lunar rocks for building colonies. Brian O'Leary.
Some of the asteroids are carbonaceous. They contain a lot of carbon, hydrogen, and nitrogen, which is completely missing in lunar samples. So we can use these materials for the space manufacturing facilities without launching them from the Earth. It would be possible to take one of these mass drivers and, with a very gentle shove, put it on an orbit to one of the Earth-approaching asteroids. This asteroid might be, 200 meters across, weighing 10 million tons. The mass driver would then rendezvous with the asteroid, glom onto it, and then would gently nudge the asteroid by Newton's third law. Little pellets would come out the back end, and it would go along very gradually for a period of, we'll say, 2 or 3, maybe 4 years, and would arrive in a high orbit around the Earth for space manufacturing, about a few million tons worth. So what we're really doing, we're talking about a scenario in which an asteroid could be lassoed from its current orbit and put into a high orbit around the Earth, and to be a new moon of the Earth.
A new moon of the Earth that could be mined and processed to make not only materials for space habitats, but also for the construction of solar power satellites. This is where O'Neill's ideas of space colonization meet with Peter Glazer's for solar power satellites. Instead of bringing everything to build satellites up from the Earth, O'Neill proposes using the resources already in space. But it's a concept that takes some getting used to.
Although logically it made very good sense, logically indeed it appeared as though power made by power satellites constructed from non-terrestrial materials might be less than half as expensive as power made from satellites launched from the Earth. That even though the logic made sense, the very idea of the use of materials from beyond the biosphere seemed so far out that one shouldn't talk about it. That is, it was felt by many people within NASA that one should continue to do things the wrong way because of the fact that it would be less startling to people.
But NASA is now taking O'Neill and his ideas increasingly seriously. O'Neill himself sees the shuttle playing a central role in his scheme to begin exploiting the resources of space. Within a few years, the shuttle could be assembling mass drivers in low Earth orbit from materials brought up from Earth. These mass drivers could then roam free in near-Earth space, fetching asteroids, sending supplies and people out to the moon or high Earth orbit to build solar power satellites and habitats for the construction workers. So integral has the shuttle become to O'Neill's plan that its former critic, now working with O'Neill, has done a complete about-face. Brian O'Leary.
I think that the O'Neill concept will save the shuttle from the fate that I first predicted. And it's simply because this concept is so enormous, and it is in its scale and the change of human events that's going to happen inevitably as a result of this. I mean, we could be wrong by a factor of 2 or 3 in the amount of material required or the cost, but that's still just negligible compared to the effect of igniting the non-terrestrial materials, nudging asteroids or retrieving lunar resources and using the constant solar energy in space. Once you've made that conceptual leap and you've removed yourself from the Earth and you're talking about just pushing things around in space with relatively low cost and low energy, then it is a totally new viewpoint that needs to be developed. And the space shuttle is just the truck we need to do what we want to do.
program, once at the level of producing a couple of satellite power stations per year, would not stop there. We would then upgrade the manufacturing capability up to the point eventually of being able to satisfy all of the world's needs for low-cost, clean electrical power. By the time we get that far, we would certainly need to have many tens of thousands of people in space, and I'm sure that they would by then be living in rather large and comfortable space habitats.
The design of space habitats is becoming a popular activity on college campuses and NASA-sponsored study groups. This is one design, a torus or donut over a mile in diameter. The sunlight is reflected by a huge overhanging mirror down into the rim of the torus. It is here in the rim that people will live and work. Inside the rim, the artificial gravity created by the rotation of the torus provides an environment for housing and for industry. An industry that, as well as supplying many of the habitat's needs, might also exploit its unique position in space to make things for export to Earth. And all important to the habitat, there must be agriculture. The colonists will have to be self-sufficient in food, and that could be a problem. This is a controlled environment agricultural experiment on Earth. It grows excellent tomatoes in very high yields. The environment is totally enclosed and totally artificial. Light is from electricity. Walls are reflective aluminum. Behind the scenes, the nutrients for the crop are fed into the water supply automatically from 3 drums. The carbon dioxide in the air is kept higher than normal to stimulate plant growth. All the water evaporated inside the enclosed unit is collected on air conditioning coils and recirculated for use again. The tomatoes themselves aren't grown in soil but in shallow troughs, where the nutrient-rich water trickles over their roots. The system can also be used for growing a crop like grass, and certainly simplifies harvesting. But even very simple, partially recycling systems like these need constant monitoring to prevent them from getting out of balance. And any sort of agricultural system in space, totally enclosed and receiving only sunlight as an input, involving dozens of components all interacting and mutually dependent, is far beyond our present capacity to devise. NASA is well aware of the problem.
Yes, NASA is considering very seriously the need to start working now on closed life support systems. While we don't have any immediate plans to launch such systems, it is quite clear that the future of manned space travel, manned space flight, manned space existence, if I can be so bold, will depend upon solving these problems.
Solving the problems for space colonies might also help us manage the ecology of Earth. Meanwhile, artists' conceptions of space colonies tend to ignore the difficulties and depict idyllic, Earth-like environments.
When you first start considering an idea as magnificent as this and as far out as this is, there's a tendency to be egocentric about it and to put in one's own experience and background. And since we're all Earth-oriented people, I think it's quite natural to paint fields and hills and birds and all those things we know. Now, whether or not it would look that way, I really can't predict. My guess is it wouldn't quite look the same. Not that it's any better or worse, but I think it would look a bit different.
Happy valleys in the sky, O'Neill's critics call his ideas for the habitation of space, and suspect he plans simply to abandon Earth and its problems altogether. But O'Neill and his supporters argue that turning to space is one of the few options we have left to help solve the problems of Earth. Henry Cole.
The best way to look after Earth is to find new space to live and new raw materials and new sources of energy. It isn't exactly as the way to look after Europe when America was discovered was to establish a colony. No one questions that now. And I think the logic is just as compelling in the case of space colonization.
Most of the people who've looked into the sociological results of staying on the surface of the Earth and not using any of the non-terrestrial resources find that we're almost sure to be driven to a much more severely limited, much more authoritarian world because of the fact that as soon as you begin making rules in one area, the physical area, it's very hard to do so without also making rules in the psychological areas as well. So that I think if one does value human freedoms, freedom of thought, freedom of action, it helps very much to be in a place where the physical freedoms are available also.
It's inevitable in terms of human population expansion to move into the universe. Jerry O'Neill predicts that within 200 years there will be more people living in space than on Earth, and I fully believe it.
Space has begun to intrigue people again, especially the young, as the huge crowds at the newly reopened Air and Space Museum in Washington have shown. It's 20 years since the space age began, almost 10 since man walked on the moon. For a whole generation, space is neither exotic nor the realm of the military-industrial complex, but simply the Earth's backyard, an environment waiting to be explored and conquered.
Ever since I was a kid, I've always saw the Earth as just a planet in space, and I've always thought of the vast reaches that were around. And I never thought that man was confined to the Earth, that this was the only place he would ever be.
People are beginning to get this new cosmic consciousness that the space program first introduced to us. And I think that we're on the verge of a second Copernican revolution. And where Copernicus comes in is that now the Earth is no longer the center for gravity space, that you can move around lots of material in space and draw a new kind of wealth from the energy and materials available in space.
And it isn't just the starry-eyed young that have begun to develop a cosmic consciousness. At Princeton University, where Jerry O'Neill is professor of physics, the third annual conference on developing the wealth of space was attended by aerospace engineers, industrialists, even sociologists. One reason for O'Neill's growing support comes from astronaut Rusty Schweikert.
I think the nice thing is that Jerry is a very solid, technical person with an excellent track record, and so it's not easy for those who are skeptics to wave their arms and cause them to disappear.
But the high point of the Princeton meeting was the first public demonstration of the MIT mass driver, running at full power.
So far we've demonstrated this mass driver during every intermission at this conference at 25 G acceleration. That's the maximum acceleration we can get at room temperature. And at that acceleration we have enough braking section to dissipate the energy and stop the vehicle. Now we're going to try for 100 G acceleration, and we do this by pre-cooling the vehicle with liquid nitrogen so that its resistivity drops by a factor of 4 to 6, and it conducts that much more current. And at that current it should produce very nearly 100 G, which was our objective.
Accelerating at 100 G means the vehicle would reach a speed of 160 miles per hour, too fast to be stopped within the rails of the mass driver itself.
What we're doing here is we're trying to make a very good brake for the machine. We don't have a brake that will stop it when it's going at the fast speeds we expect. So we just built this box here, a wooden box, and it has lead bricks in the front. And the reason we put the bricks in there is to give it much more mass. When it hits, it won't slide forward and go out the wind or anything. The lead bricks will definitely stop it. Pick it up. Okay, let's see how it feels through this glove.
For Kevin Fine and the other MIT graduate students, it was a tense moment. Would the vehicle work at all at minus 200 degrees Celsius?
It feels just like it does when you stick it in there without being cold. It bends the same way. Slides fine, no problem at all.
Everybody's ready, Bill? Ready? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. Just a second, folks. I'm going to calculate the acceleration on that one over here. Can we see that again?
Derail. Yeah, what's right?
5, 4, 3, 2, 1, 0. I calculated the acceleration. It seems that we still have some problems. We only got 33 Gs on that shot. Just 33. We'll keep working at it.
After all, this is a very first try and a very simple experiment, but if we fix the mechanical triggering problems, I'm sure that we'll get our 100 Gs.
I think that this model and the G-forces that it's packing is just what we need. And now all we need to do is do it for a few more meters. The length of the one that would retrieve the asteroid would be, let's say, a few hundred meters long at that acceleration level, and that's all you need.
The power, the sort of leverage embodied in the mass driver is an extremely important thing, and the fact that it has been demonstrated at this very simple level, I think, is a very subtle but powerful influence on the way the initial concept will be received, especially by technical people.
I think there's a bit of history about what's happening today.